Okay, so I'm going to talk briefly about electronegativity and polarity. You may have had this term introduced to you before this year, but I'll explain exactly what electronegativity means, and I'll firstly link it to ionization enthalpy, because that should be a term that you're familiar with. We need to know about trends in electronegativity across the periodic table, essentially that it increases as you go to the top right of the periodic table, and we need to be able to predict the polarity of a bond based on the electronegativity of the two atoms within that bond. Once we can do that, and we can determine whether bonds are polar or not, we can then see if molecules are polar. And the way that this is going to work is that it's going to link into our understanding of intermolecular bonds that can form between molecules that we'll do in subsequent lessons. So firstly, a bit of a reminder on first ionization enthalpy. Hopefully you remember that first ionization enthalpy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms of an element. So we're looking at the outer shell electrons and the amount of energy that it requires for those to be removed, or for the first one to be removed. Now going across a period, so as we go for instance from lithium to beryllium and all the way across to neon, what's happening there is that we're adding protons. We're adding electrons as well, but they're going into the same outer shell, so they're not really shielding outer shell electrons from the feel of that extra nuclear charge. So the outer shell electrons are more tightly held. Therefore, it takes more energy to remove one of those. So across a period, the first ionization enthalpy increases. Now going down a group, so as we go say from lithium to potassium, lithium to sodium to potassium to rubidium, etc., ionization enthalpy decreases. Now going down a group, so if we go from lithium to sodium, although we've added another 8 protons into the nucleus, we've added another 8 inner shell electrons that effectively cancel out that increase in nuclear charge. However, going from lithium to sodium, outer shell electrons are now far further from the nucleus because there's a whole extra shell, so they're less tightly held because they're further from the nucleus. So going down a group, first ionization enthalpy decreases. Going across a period, first ionization enthalpy increases. So we can essentially say that the trend is, as you go towards the top right of the periodic table, as this nice graphic shows here, the attraction of outer shell electrons increases. Now why is this important? Well, it's important when we think about covalent bonds. And this is where this concept of electronegativity comes in, and essentially it's exactly the same thing as ionization enthalpy. Now if you consider a covalent bond between atoms of 2 elements, the electron density is probably not shared equally. Now this is because, as we've seen, different elements have different extents of attraction for their outer shell electrons, and the outer shell electrons include bonding electron pairs. So different elements have different abilities to attract bonding electron pairs, and electronegativity is this measure of an atom's ability to attract a bonding pair of electrons. It's important to know that definition by rote. And if you have a look at these arrows here, this is indicating to us that electronegativity, just like first ionization enthalpy, increases as you go towards the top right hand corner of the periodic table. Now you notice a couple of things here. Firstly, there are some numbers given to these values. You don't need to know these numbers, but it's a good idea to have a feeling for some of them. If you were given numbers in an exam, you could work out differences in electronegativities, and as you'll see in a second, that will enable us to work out whether a bond is polar or not. But the scale that those numbers are on is the Pauling scale. That's after Linus Pauling, 2 times Nobel Prize winner. Only one in chemistry though, the other one was a Nobel Peace Prize. And you can see that fluorine is the most electronegative element, with an electronegativity value of 4. Other electronegative elements, the nitrogens, oxygens, chlorines, they're grouped around fluorine up here. You can see carbon and hydrogen have a very similar electronegativity of 2.2 and 2.6. We don't really consider they have a difference in electronegativity, which is important when you consider alkanes, for instance, being non-polar molecules. You'll notice also that the noble gases don't have an electronegativity value, and that's linked to the definition here that electronegativity is a measure of an atom's ability to attract a bonding pair of electrons. But if you remember, these guys don't form bonds, so that's why they don't have electronegativity values. And this is another graphic showing it, so again it's increasing as we go towards the top right hand corner of the periodic table. So an atom's ability to attract bonding electrons increases as you go up in this direction. So if we look at a simple covalent bond, so we've got atoms A and B here. If you've got atoms A and B that have the same electronegativity, the bonding pair of electrons is going to be shared equally between them. You'll have a perfect covalent bond, or a non-polar covalent bond, should we say. If, though, in this case here, B is more electronegative than A, B will have, on average, a greater share of the electrons than A. What that means is that atom B will become partially negatively charged. And you can see the symbol here. This is a lowercase Greek letter delta, so it'll be delta minus, so it has a partial negative charge, whereas atom A will have a partial positive charge. And you can see this funny symbol here with this arrow and then this cross line here that's slightly more towards the left-hand side of it, that shows that this bond here has a dipole or is polar. So it just means it's a separation of charge, and one end is negative, one end is positive. Now actually, if you've got a very big electronegativity difference between B and A, it might be the case that B completely rips away the electrons from A. Now if that were to happen, you form ions. So essentially, if you think about it, ionic bonding and covalent bonding are really two extremes of a scale. If you've got equal sharing of electrons, you'll have covalent bonding. Whereas if you've got one element that's far more electronegative than another, you'll have ionic bonding. Now if you think about it, if we go back to a periodic table and we look at here, now we've seen, for instance, sodium chloride before being an ionic compound. Well, sodium has an electronegativity value here of 0.9 and chlorine 3. Now that's a big difference in electronegativity. So if these guys were to try to form a covalent bond, the chlorine has a far greater pulling power, if you like, for the outer shell electrons, and would rip an electron away from sodium. So that's why it forms an ionic bond. So it's just another way to think about it, rather than just say metals and non-metals forming ionic bonds, for no good reason. So now we can see, or now we can work out, rather, whether a bond is going to be polar in a molecule. You simply need to know the electronegativity values. The more electronegative element adopts a delta minus charge, the more electropositive one adopts a delta plus charge. And unless they've got exactly the same electronegativity, the bond will be polar to some extent. Now that doesn't necessarily mean that a molecule that contains polar bonds will be polar. And it's important to distinguish between polar bonds and polar molecules. So just to recap, a polar bond then is a covalent bond where there's a separation of charge between one end and the other. So one end is slightly positive, one end is slightly negative. The polarity of a molecule, so for a molecule to be polar overall, it needs to have one end that's negative or slightly negative, and one end that's slightly positive or positive. So the polarity of a molecule is a combination of all the bond polarities and takes into account its shape. So if we look, for instance, at something like this, tetrachloromethane. Now, tetrachloromethane's got 4 polar bonds. So you can see here delta plus, delta minus, delta plus, delta minus, delta plus, delta minus. The molecule as a whole, though, is not polar since it's symmetrical. And this will be a general rule. If a molecule contains polar bonds but is symmetrical, they will cancel out. Because you can see here it doesn't have one end that's slightly negative and one end that's slightly positive. The polarities of the 4 bonds cancel out. A fancy way of saying this is that the centre of the positive charge, which would be at the centre of the molecule here, is coincident or at the same place as the centre of the negative charge, which again would be the centre of the molecule. If you look at something like, where's my pointer? If you look at this molecule down here, though, so this would be trichloromethane. Now, trichloromethane, if you look at the shape of it, again, it's a tetrahedral shape. But now look at the bond polarities. If we look here, we've now got delta minus, delta minus, delta minus, but now delta plus here. What we effectively have, we have one side of the molecule that's slightly negatively charged, and one side or end of the molecule that's slightly positively charged. Now we have a polar molecule. So we have a separation of charge, one end that's slightly positive, one end that's slightly negative. So because this is asymmetrical, this is now a polar molecule. And just a little note here that I don't really think this this definition will come up on your syllabus. But if you wanted to know exactly how polar a molecule is, you can measure it by something called its dipole moment, which is the charge difference, because obviously the amount of positive and the amount of negative can differ, times by the distance between the separation of those charges. Now, therefore, in order to work out whether a molecule is polar overall, you need to know if the bonds are polar, and you need to know about its shape, and consider if any of those bond polarities cancel out. So just briefly, we'll do some work on this in the lesson. Hopefully you remember your shapes of molecules. So you remember that it's all based on this valence shell electron pair repulsion theory, and you look for the number of regions of electron density around the central atom. So if you've got two regions of electron density, and remember those could be bonding pairs of electrons, they could be lone pairs of electrons, or they could be double bonds, etc. If you've got two regions of electron density, they repel each other to a position of maximum separation, or to minimize the electronic repulsion, and will adopt this linear shape here with a bond angle of 180 degrees. If you've got 3, then the shape is trigonal planar with a 120 degree bond angle, so this is flat, and then 360 divided by 3 would be 120. If you've got 4, it's this tetrahedral shape. You can just say 109 for the bond angle there, but you do need to remember that one. If you've got 5, well, it's trigonal bipyramidal, so you see this trigonal structure in the middle, so it's like a flat 3-pronged structure in the middle, and then one above and one below. The bond angle here is at 90 degrees, but within the flat trigonal planar shape in the middle is still 120. And then if you've got 6 regions of electron density, then it will adopt an octahedral shape. Just for completion while we're here, remember if there's lone pairs, they modify the bond angles. So remember, lone pairs repel lone pairs more than lone pairs repel bonding pairs, which repel more than bonding pairs repel bonding pairs. That's a bit of a mouthful. And as you can see here, for instance, if you've got methane, it's got that bond angle of 109 or 109.5. But if you look at ammonia, well, the shape of ammonia is based on a tetrahedron, because it's got 4 regions of electron density. But because one of those regions of electron density is a lone pair, we describe the shape as being trigonal pyramidal, and the lone pair repels more than a bonding pair, so compresses these bond angles in slightly to 107. In water, and I assume that's going to be the next example, there we go. So in water, you've got 2 bonding pairs, and it compresses it more. Now again, the shape is based on a tetrahedron, so it's near to 109, the bond angle, but now actually, because you're just left with 2 of the prongs of the tetrahedron, that's a bent linear shape. Okay, right. So in the lesson then, we'll do some examples where I'll ask you to pick out whether bonds are polar or not, and whether molecules as a whole are polar.